Good afternoon, everyone. My name is Kusmartseva of Loughborough University in the UK, and today I would like to present to you some of our recent work on Rashba metasurfaces, which have a very interesting property of perfect darkness. This type of behavior is useful in systems where you would like to minimize light losses due to reflection. One such use is anti-reflective coating or arc industry. The global arc market is very, very big and keeps growing as our need for this type of equipment and devices is constantly increasing. The three most dominant sectors utilizing arcs, anti-reflective coatings, is the energy sector. When we are creating solar cell panels, again, we want to minimize reflection light losses so that we can convert more of the light into energy. Personal equipment such as cameras and glasses and eyewear, again, arcs are very, very important. Rather limited use of arc is in the communications industry, but that's getting more and more expanded as we're trying to detect very low signals, and we definitely want to reduce reflection in this case. Commercially, the way anti-reflective coatings are realized is using a multi-layer approach. In this approach, you take two different materials with different refractive indices, usually high and low, and you stack them one on top of each other, creating a kind of sandwich structure. And by doing this, you can achieve very good performances. So somewhere between 0.5 and 2% reflection across the visible light range, 400 to 700 nanometers. In the research, anti-reflective coatings are a very, very big field. I have chosen some specific examples which illustrate the interest in very thin anti-reflective coatings. Research groups have shown that if we take a mirror and put a very thin layer of a semiconductor on top of it, such as germanium, we can achieve a fairly low reflectance of 0.2% at a specific wavelength. Other groups have inverted the structure and they've put a very, very thin layer of metal nanoparticles, 10 nanometers of metal nanoparticles on top of a semiconductor. And again, they have seen that they can achieve very low reflectances at specific wavelengths. So there's clearly something about thin film structures which is very beneficial for to minimize reflection. What could this be? It could be very interesting to investigate the link between the dimensionality of the films and single films and the optical properties and reflectivity in particular as being one of possible applications. The premise for this work is, can we shrink the conventional approach using multi-layer systems into something that is very thin, potentially even 1 nanometer thick? Thin films have clearly shown potential in that direction, but can we reduce the thickness of the thin film coating even further and still maintain the high performance across anti-reflection? One other way to think about it is, if we look at a conventional multi-layer structure, it can be up to 400 nanometers thick, so clearly a very bulk object. When we reduce the film so thin at a certain thickness, the surface and the bulk of the film start to behave differently, and the optical properties at the surface and inside of the bulk of the thin film are different. So in that case, one single layer starts to act as a multi-layer, simply because the disparity between surface and bulk. So there is some potential to achieve a very similar multi-layer effect, but when we reduce the film to nanometer scale. In this work, we decided to fabricate anti-reflective metasurfaces, or MS arcs. So we have taken dielectric, which is usually some type of oxide, silicon oxide or alumina evaporated onto a substrate such as silicon, and then deposited using the electron beam technique a very thin metal nanofilm on the surface of the dielectric. The thickness of the film went from 0.2 to 25 nanometers, and we have used a wide range of different metals, going from niobium and tin and bismuth down to noble metals such as gold and platinum. So our structure was very, very simple. In the case of the tin MS arcs, we needed to include a 1 nanometer thick layer of germanium to achieve a nice wetting layer across the interface. This is what we wanted to synthesize. When we have investigated the morphology of the MS arc, they were quite diverse. Here are some examples of 4 different species: bismuth, niobium, silver and platinum. They all have different thicknesses, and the morphology clearly depends on the thickness of the film. When the film is very, very thin, such as 2 nanometers, the granular islands are very small. The scale bar here is 50 nanometers. As we increase the thickness of the film, the grains keep growing and growing, eventually starting to get bigger. You can see that the grains start to merge together, forming interconnected islands, and then as the film becomes very thick, like 10 nanometers, it's almost like bulk. You don't see the granularity so much anymore. When we have measured the optical properties and specifically the reflectivity of the MS arcs, we found a very interesting behavior which was repeated across all systems. Here I'm going to demonstrate the properties found in bismuth MS arcs. We have varied the thickness of the bismuth from 0 to 9 nanometers, and interestingly we found that a very critical thickness of the bismuth nanofilm, between 6 and 7 nanometers, we have observed 2 regions of 0 reflectivity across the visible light spectrum. You can see it better in the color diagrams here. The blue corresponds to 0 reflectivity and the red is 14% on this particular scale. Again, this was very, very clear effect, and it does persist across a narrow window of wavelength. This is also seen in other MS arcs. We have tried different metals going from tin to platinum. All of them illustrate a minimum. In some cases, two minima, like the bismuth. In other cases, only one, like for example the niobium or the platinum. The 0 reflectivity regions are shown in pale green here. So there is a particular thickness of the metal where 0 reflectivity behavior or perfect darkness is observed. It seems to be universal, metal independent. In both cases the oxide was the same, silicon or alumina. The effect is localized to a particular range of wavelength here, listed in this table. We have tried to model these structures using plane waves and Fresnel theory. Here is a schematic diagram of our structure. We had a substrate, an oxide, a metal film, and then of course the air, the interface. So we've modeled the whole thing as an effective structure with an effective refractive index. The optical constants were obtained, N and K were obtained through the reflectivity experiments and also modeled theoretically. Here we show the result of the theoretical modeling. The black region corresponds to 0 reflectivity. It is observed in all our systems going from niobium, platinum, bismuth, tin and silver. And interestingly, the values for the optical constants N and K obtained through theoretical modeling that correspond to the zero reflectivity position agree completely. There's a complete agreement between theory and experiment. We didn't use any fitting parameters, We just had complete agreement between the experiment and the theory, which again corroborated our premise that the properties we are seeing are universal and they definitely have some kind of physics underlying this behavior, which gave rise to several questions. Why do we observe this zero reflectivity perfect darkness phenomena in these structures? Is the origin potentially structural due to some kind of surface morphology, or is it electronic, or is it just simply optical and absorption? So these are the three possible origins, and we tried to construct a series of experiments to try and investigate what could it be. Just a little addition. The thickness of the metal nanofilm, 1 to 10 nanometers, is much less than the wavelength, and therefore the length of the optical path is not really affected by the presence of this film, which kind of tries to rule out the reason that it could be optical. Maybe we need to decide if the origin for perfect darkness is structural, due to surface morphology, or electronic, in other words, quantum. To study the morphology, we've used atomic force microscopy, and we looked at the roughness on the surface of these films. Here is an example of a niobium MS arc. Two cases are shown over here: 10 nanometers, which is the critical thickness, the thickness where zero reflectivity is observed, and 135 nanometers, which is clearly bulk niobium, so it's effectively a poor mirror. We've done various line scans across different positions in the samples, and the cross-sectional pattern is shown in the trace diagram over here. Unsurprisingly, we see that the surface roughness depends on the thickness of the film. In very, very thin films, the surface roughness is very small. Only variations of 2 nanometers are seen on the trace scan. As the thickness is increased, the variation in the Z position increases, going from 3 nanometers to 4 nanometers. But across the whole range, the change is not very big, 2 to 4 nanometers. And the variation in the Z position is stronger than in the XY. And even then, it's not significant enough. Our second premise was to see, could it be something electronic that is responsible for this behavior? So we have, in the first instance, we have performed Raman spectroscopy on the tin MS arcs and tried to see if we can correlate the phonon behavior to anything related to the optics. Here is an example of a Raman spectra for germanium tin MS arc at the critical thickness where zero reflectivity is observed. We see 2 modes that are related to the tin and 2 modes that are related to germanium. And we have tried to follow the behavior of the spectra across the thickness of the MS arcs, and we have notably found very interesting behavior. We found that the longitudinal modes of the tin and the germanium, the black and the green on the graph, are practically invariant to the thickness of the film. However, the transverse modes, which are the red diamonds and the pink stars and the triangles here, are very, very sensitive to the thickness of the film. And what was even more impressive is that when we reached the critical thickness of the tin, where zero reflectivity and perfect darkness were observed, we saw that there is a particular maximum in the ratio of the peak intensity of the different modes, suggesting that at that thickness there is a very specific correlation between different types of vibrations present in the system. And we seem to think that this is probably a manifestation of the surface states that form on the surface of the film. And the thickness, of course, relates to the percolation effect that occurs on the surface. Finally, to probe the electronic properties, we have conducted an impedance spectroscopy, which is to say that we've sent an AC current through the system and tried to investigate the granularity that is present there. And what we have observed is that, again, at the critical thickness of the thin film, which is 10 nanometers in the case of niobium MSArc, the behavior of the impedance is very strongly dependent on any kind of gating voltage that is present. Whereas at the far away from the critical thickness, the behavior is independent of the gating voltage. And this suggests that at the critical thickness we have a continuum of electronic states forming on the surface that can be sensitive to motion of electrons. And we suspect that this is the 2D electron gas. So what is the origin for the perfect darkness properties in the MSArc? We believe that the oxide in our system is acting as a Farbey-Perot resonator, and the surface of the film, the metal nanofilm, segregates into a surface and bulk, creating a multi-layer structure, an intrinsic multi-layer structure. The surface states on the top are created due to Rashba interaction and the strain due to the roughness and the deformation, where roughness and deformation do play a role, but not only. The surface regions, the surface state regions have negative refractive index and equals less than 0. And as a result, when you try to send light through the entire structure, there's a Vesilago lensing effect, and the light is focused inside with 0 reflection. The reason why this negative refractive index zone forms is possibly due to the arising of an electron gas, a two-dimensional electron gas system that occurs when the surface states reach a certain level of percolation, which again is controlled by the thickness. And here are the conclusions. We believe the MSArcs are quite interesting approach to realize 0 reflectivity. They are metal independent, which means that they have very big application spectrum. At the heart of this phenomenon is the Rashba interaction, which is related to the strain on the surface and the surface states that form due to the surface and the electronic phases that they sustain. Here are the collaborations with which this work was done, specifically the Khalifa University in the Emirates, Microsystems and Terahertz Research Center in China, and the Princess Noor bint Abdul Rahman University in Saudi Arabia. And thank you for your attention. Any questions?